The best place to position nuclear weapons is actually in the Great Lakes. ICBMs for launching nuclear weapons should be put on submarines powered by hydrogen and oxygen based in Lake Michigan in the United States, and if Canada would agree, Lake Superior and Lake Huron. The lake surfaces do not freeze in winter, so ice is not a problem when launching. The area of the lakes is so large that the submarines cannot be targeted by nuclear weapons. The problem is that there is a fishing industry in the lakes, and the presence of the submarines may interfere with their ability to use nets and other forms of fish harvesting. The missiles used would be extended range versions of the Navy Trident missile. The simplest way of extending the range is to reduce the number of warheads from 6 to 3, and that could be 2 warheads and 1 dispenser of hard shaft, pieces of aluminum to jam radar. The weight saved from the warheads that are removed can then be used to add additional propellant in the final stage without increasing the overall weight of the missile. That would then have a significant increase in the range of the missiles launched. If necessary, a larger missile than that could be built. If the additional propellant weight gained and the additional velocity gained from removing the warheads is not enough to give adequate range to cover target area for the missiles, then a larger missile would have to be built. Because the areas between the United States and Canada, the lakes can be easily secured against surveillance. In addition, they're too large to target with nuclear weapons, so you cannot just fire nuclear weapons into them in an attempt to destroy the submarines. The submarines would leave their bases and remain at sea probably for 1 or 2 weeks, and then return to base, and possibly exchange crews, and then sail again. Nuclear reactors would probably be unacceptable on the submarines owing to the danger of some radiation leaks, but using hydrogen and oxygen in compressed cylinders alongside the hull would provide a significant amount of extended range. 1 kilogram of hydrogen produces an energy equivalent of about 32 kilowatt hours of power. Allowing for inefficiencies, that should be at least 20 kilowatt hours of power that can actually be used. Air at sea level weighs about 1/12 of a pound per cubic foot. Hydrogen would weigh somewhere between 1/14th and 1/15th that, or about 1/180th of a pound per cubic foot. If it is compressed to 6,000 psi, that is about 400 atmospheres, or about 2.2 pounds per cubic foot, or about 1 kilogram per cubic foot. If 500 horsepower is needed to operate the submarine for routine service, that would be about 650 kilowatts, or so you need about 32 cubic feet of compressed hydrogen per hour of operation. If you wanted to have at least 30 days of operating ability, that is 32 times 24 times 30, or about 24,000 cubic feet. If the cylinders of compressed gas are 20 feet in diameter, that will be about 300 square feet. One on each side is 600 square feet. If it goes for 200 feet, that's about 60,000 cubic feet, or enough for about 2.5 months of operation. In addition, you need oxygen, and the oxygen would be about half the volume of the hydrogen. So if the hydrogen cylinders are 200 feet long, you need oxygen cylinders an additional 100 feet long, giving an overall length of the submarine of perhaps 400 feet. The water produced by the hydrogen and oxygen being reacted in a fuel cell would also be used for drinking water. Additional drinking water supplies may be carried along as well. The crew would be at the rear of the submarine where the motors and the fuel cells are. The missile tubes would all be forward. It would be a very simplified design, basically just a big long tube with the hydrogen and oxygen cylinders hung on either side. The submarine would leave its base, travel some distance, and then settle onto the lake floor. From time to time, it would rise up and then move to an additional position, and again, settle on the lake floor. This makes it difficult to identify where it is, makes it pretty much invulnerable to attack, and provides a secure deterrent to any strike against the United States. The Trident II D4 missile has a range something in excess of 4,600 statute miles. The old MX missile had a range in excess of 6,000 miles. If it was desired to cover the entirety of China from the Great Lakes, a range something on the order of 8,000 miles is needed, 7,500 to 8,000 miles. That means a higher velocity is needed for the upper stage, which has the nuclear warheads. By reducing the number of warheads carried, by increasing the fuel load in the upper stage, and by adding either a larger first stage, increasing the sizes of the additional stages, this range could be achieved. One would have a very large missile, which would require a very large submarine hull, but it can be built. The missile tubes would all be forward. The crew would be at the rear of the submarine with the fuel cells, the operating machinery, and the launch controls. This produces a fairly compact, efficient design of submarine. It doesn't have to go very fast. A top speed of even 10 knots would be acceptable. It could carry 20 to 40 missiles, whatever is desirable in terms of the number of submarines and the number of locations at which they can be hit at any given time. The Trident II missile is under 45 feet long. This missile would be something over 50 feet and maybe approaching 60 feet in length. The MX missile was 71 feet long, somewhat different design, and it carried 10 warheads. The other factor that comes into play is that the actual curvature of the Earth. 12,000 miles represents the point from one point on the Earth to the exact opposite point of the Earth. So 12,000 miles would mean that you sweep over the entire Earth, going from one end to the other, for instance from the North Pole to the South Pole. As you increase the range of the missile, the angle with which the warheads fall into the Earth's atmosphere decreases. It goes from being a very steep drop to a shallower drop. If you wanted to launch a missile for 12,000 miles, it would be glancing down through the Earth's atmosphere and skimming the Earth to make contact. At 8,000 miles, it is going to travel through more Earth's atmosphere at a shallower angle, and there's going to be some more deflection and some reduction in accuracy.